Okay, guys, so here's the solution for the exam. We're going to go over this, and you're going to realize that this test was a lot easier than you thought. But let's go through it. Okay, so first question is asking, in the space below, provide the chemical formula and the name of the compound that was added to your indicator, and what was the color of the indicator. Okay, so this one's actually pretty simple, depending on whatever formula you used. For example, I think one of the acids was H2SO4, and then one of the bases was NaOH. I'm going to just use these two as an example. So you're supposed to give me that chemical formula, right? You're supposed to give me the chemical formula of each. And then you're going to tell me this is called sulfuric acid, and your indicator should have turned pink. Pink color appeared. This was a give me question. This was simply following the instructions, telling you to give the name of the compound, right? You had to name it, provide the chemical formula, and then what color was observed. You needed those three things to get full credit. NaOH, this is sodium hydroxide. All right, and this should have turned green color. Green color observed. That's literally all you had to do for the first one. That had to do with the experiment that you did in class, and that was it. If you did all of that, then you received a score of 100%. 100 for this one, and 100 for this one, to give you an overall score for that question of 100%. Okay, question number 2 says the compound oxalic acid is an organic acid that forms a white crystalline. Oxalic acid is toxic and it belongs to the family of carboxylic acids. Okay, so the first question says, what would be the chemical formula for oxalic acid? Okay, so I can see right here that this is going to be a oxy acid, right? So if I know it's an oxy acid, then I have to start looking at my polyatomic ions. Sorry, I was blanking there for a second. I have to start looking at my polyatomic ions. Now, I know that oxalate, right? Oxalate is a polyatomic ion, and because it ends with the ATE, it's going to end with the IC ending here. So oxalate is C2O4, 2 minus. Okay? Now, I know what a lot of you guys did is you went online, you looked at the chemical formula, then you wrote it in your test, and a lot of you guys wrote this. Okay? If you wrote that, you got most of your credit, but you didn't get full credit because you looked it up, right? So the way I wanted it was for you to look at it, to write it, and look at it like this. Okay, so I'm going to use this space. I know that H is a 1 plus, oxalate is a 2 minus, this comes down here, this comes down here, and because acids have their hydrogens out front, then you should have wrote it like this. If you wrote it like this, then that tells me that you actually went through the process and you did the compound. If you looked it up and you wrote it the other way, I knew you looked it up. So you didn't get full credit for that. So showing me this process or showing me the correct chemical formula, that gets you 100% of the points. Okay. Explain why this is considered a covalent compound and provide the IUPAC name. Okay, so this is a covalent compound for the reasons that all elements are nonmetals. Right? All the elements are nonmetals. So if all your elements are nonmetals, then it's going to form a covalent compound, right? Now, it says also to provide the IUPAC name. Now, a lot of you guys, not a lot of you guys, but a lot of you, most of you, some of you, went on Google and looked up IUPAC name for this acid, and you came back with like ethanoic acid or something like that. Guys, I didn't teach you that. I told you it'd be obvious when I know you guys were. You're not technically cheating, right? Because I gave you the time and the space to look that stuff up. But I wanted you guys to use the rules that we learned in class to name it. So when you don't do that, it's really obvious, right? So because this is a covalent compound, then you should have named it something along the lines of dihydrogen because there's 2 hydrogens. Dicarbon tetroxide. All right. This was in your notes. We had just gone over this. I also reviewed this in tutoring. If you did it in this process, right, you got 100% for that, and overall you got 100% for that question. If you gave me this formula, right, and gave me the Google name for the IUPAC name for this oxalic acid, then you didn't get full credit, and in some cases you didn't get any credit at all. I tried to give you as much as I could, but when you're just copy pasting, you're not going to get a lot of credit. Okay, so that was number 2. Those were 2 very simple questions. If you had reviewed your polyatomic ions and gone through the process, this should have been 2 easy hundreds. Okay, one of the elements in the oxalic acid is carbon. Below, you'll find the carbon and the relative abundances of its isotopes. Using the information below, justify why carbon has an atomic mass of 12.01. You must show your work for full credit. This was a calculation. Okay, so if you didn't show me a calculation, you got minimal credit, 1 out of 4 points or 25%. Depending on what you wrote, you either got a 25 or a 20%, but this is how you solve this problem. So here are my relative abundances for each one, okay? These are my isotopes right here, right? These are this is the mass of the atom changing in response to becoming a different isotope. So the atomic mass for the first one is 12, and that exists at a 98.9% abundancy. So if I was to write the percentage as a decimal, it would be 0.989. If you multiply that out, you're going to end up with 11.868. Okay. The next one is carbon-13. That has an atomic mass of 13. If you multiply that by its decimal, you should end up with 0.011. If you multiply that out, you're going to end up with 1.143. And the last one is carbon-14. That exists at a very, very small amount. But if you multiply it by its percentage into a decimal, you're going to end up with, sorry, that was a mistake. Okay, there we go. Let's see, 1, 2, 4, 5, 1. Then you're going to end up with, right? Okay, if you add all these guys up, you end up with 12.011014, and you had to justify why the atomic mass was 12.01. There it is. Okay, we carried a few extra decimals because you want to be as precise as possible, but this was the calculation that I was looking for. We did this in class. You should have had notes on this. We did it with magnesium, I believe, is the example that we used. But this is what I was looking for this question. It's taking something that we've already learned and applying it to a different element. Okay, if you did this, you got full credit. If you didn't do this, you lost points. Explain the differences between these 3 isotopes. Well, the difference is the mass changes. In response to the difference in neutrons. Isotopes, right? And I'm going to carry it on here. Isotopes have the same number of protons, but different number of neutrons. That's it. That's all you have to do for that one. If you did that, then you got a full 100% for this question. Okay? That's how you answer that question. That's what you were supposed to do. You're supposed to just give me this calculation and then tell me that the difference between one isotope and the other is a different number of neutrons, right? Again, this was in your notebook. We did this with the marbles. We did this at the example. This should have been another really easy 100. Okay, this one right here, we did this ad nauseum. I still had people that were making mistakes on this, but let's see what the question says. In the space below, give the electron configuration for iodine and provide the following information. Okay, so iodine is element number 53. It's in the 5th period, and it's in the P block. So I know I'm going to go at least up to here, right? So let's go through it. So 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, right? 5s2, 4d10, 5p1, 2, 3, 4, 5. Right here. This is your configuration for iodine. Okay? I have people going all the way up here. I have no idea why. Remember that if iodine is number 53, then here in all this electron configuration, you should have 53 electrons, right? So if you would have double counted, you would have seen that if you have more or less than 53, you were incorrect. You also have periodic tables in your notes that showed you the blocks, so you should have known that iodine should end up in the P block, which is what it is right here, in the 5th energy level, so you can always double check your work that way. Okay, number of protons, that should have been pretty easy. It's 53. Number of electrons, those are the same. Number of neutrons is you take the atomic mass, which for iodine is 126.9, minus 53. You should have ended up with 74 neutrons. And then the atomic mass is right here. If you did that, most of you did pretty good on this one, then you got 100% for this question. Okay? All right. Now, for the back page, let's see. There we go. Done. Okay. For the back page, it says, let's analyze and draw the Bohr model, the Lewis dot model for iodine. Okay. Again, a lot of you guys went on Google, searched up the diagram, put it there. If you did that, that's fine. I went ahead and gave you credit. So the Bohr model for iodine, and I'm not going to go through the whole thing because this video is getting kind of long already. If I can get it here for my pen to start working. There we go. Okay, so iodine is in the 5th energy level, so you should have at least 5 rings. Five, okay? In the first ring, you should have 2 electrons. In the second ring, you should have 8. In the third ring, you should have 8. In the fourth ring, you should have 18. And in the 5th ring, you should have 17 electrons, right? If you did that and then you got your Lewis model, your Lewis dot model, then you got full credit. Remember, the Lewis model shows you the number of valence electrons, so the ones in the outermost shell. Remember that in the outermost shell, you have the 5s, the 4d, and the 5p, right? In the 5s, you have 2, in this one you have 10, and in this one you have 5. Remember that valence electrons are the ones in the highest energy level. So even though these still exist in this shell, they're actually 1 energy level lower. So when you draw the Lewis dot model, you should have only had 7 valence electrons. If you did that, you got full credit. Okay, I'm going to go ahead and go out to the notebook because we're going to use the graphs to answer the following questions. It says, based on the models, would you expect iodine to oxidize or reduce? Justify your answer with your model and the first ionization energy. Okay, so let's go ahead and go out here. Okay, let's look up. Now, in your notebook, you should have had your first ionization energy graph, which in this case is this one right here. Right? This is the one we're going to be looking at right now. Okay? Now, let's take a look at iodine. Iodine is going to be beyond this graph, right? But iodine has the same properties as chlorine, has the same properties as fluorine. Okay? Looking at the beginning of a period and at the end of the period compared to those elements, group 17 elements are going to have a pretty high ionization energy, right? What does that mean? Ionization energy, right, is the energy required to remove an electron. Now, by removing an electron, what you do is you cause it to ionize, right? You cause it to ionize. That's why it's called the first ionization energy. It's the energy required to move that first electron and make it into an ion. Now, if you have high ionization energy, right, it means it takes more energy to remove an electron. Right? If it takes more energy to remove an electron, that means that you want to keep your electrons, right? If you want to keep your electrons, you're not going to let go. You're not going to oxidize. You're going to reduce, right? Because if you have a high ionization energy, you're not going to let go of your electrons, right? And that means that you're going to be in a position when you do ionize that you're going to pick up electrons as opposed to dropping them off, right? So the first question is asking, based on the models, would you expect iodine to oxidize or reduce? We just answered that because it's a group 17 element, right? And it has the same properties as these guys. You should be able to determine that it's going to reduce, right? Now, using the graph, right, how do we explain this? Okay, so a simple statement like, iodine, as a group 17 element, has high ionization energy, meaning it's not going to drop electrons and will gain electrons to ionize. Iodine will reduce, right? Now, it also says here with your model, oh, there it is. So you justified it now with your model and your first ionization energy. Looking at your model here, you can see that it already has 7 valence electrons. Right? On the Lewis dot model, you can see that it has 7 valence electrons. So if it wants to get to a full shell, it's going to be easier to pick up 1 electron than to drop 7 more, right? So using the model and the first ionization energy, that explanation would have got you 100% on that question, okay? These graphs should have been in your notebook. And if you look at them, it makes it a little bit easier to see what's going on, okay? Now, again, we did analyses on these. We did Edpuzzles, not Edpuzzles, but Socratives on these trends, and it's in your notes, right? Not only were they in your notes, you also had time in between test days to research this stuff, ask me questions, look it up. A lot of you didn't. This is where everybody struggled the most. How would you compare atomic radius of iodine to oxygen? Okay, so this one right here is your atomic radius. This is the graph that deals with atomic radius. All right, so if we took at iodine, which may not be on here. Yep, it's right here. Here's your iodine radius, right? And then oxygen is down here, right? So going from here to here, right, you can see that the radius of iodine, all right, this is number 4A, this is 4B. Radius of iodine is greater. Now, if you gave me this answer, right, you got minimum points. Obviously, it's going to be bigger, okay? Why is it going to be bigger? Well, if you draw the Bohr models of oxygen, all right, oxygen is in the second energy level. And iodine, we just drew on this model up here, right, has 5 energy levels. So because iodine has more shells, right, it will have a much greater distance from the nucleus to the edge of the valence shell. That's all you had to tell me, right, to get full credit on that. Using your graph, you can see that it's bigger, and the reason why it's bigger, right, is because as you go down from one period to the next, you're adding a new energy level, okay? A new shell. As you add more shells, the distance from the center to the outermost shell gets bigger, right? And in your notes, you should have also had that on the periodic table that atomic radius increases to the left and it increases down, right? Because I told you guys specifically to draw that on your graph, on your paper. Okay? Last question for this one says, based on the configuration, what would you infer about the electronegativity of iodine? Well, in your definitions, you should have had the definition for electronegativity. And to sum it up, electronegativity is the affinity to gain another electron, right? To attract unpaired electrons. So if we see that iodine has a high ionization energy and it's going to reduce, then you can infer that the electronegativity of it would be greater, right? So you can use that in your graph as well, because if you look at here, right, this are your group 17 elements, right? This one right here is fluorine, this is chlorine, and right here is bromine. Now, you don't have iodine, which is fine, because you can see that in every single one of these graphs, the group 17 element is the highest one for that period, right? The start of the period is here. It's lithium, right? So from the beginning of the period to the end of the period, the group 17 element has the highest amount of electronegativity. What that tells me is that because it's so close to having a full shell, it's going to have a huge electronegativity because it wants to attract an electron. That is why iodine will reduce. It has a high ionization energy. It has a high electronegativity, so it's going to want to pick up that electron. Again, that was in your graph. Okay? All right, for the final question here, iodine is an element found in iodate compound. What would form if iodate bonded with this particular compound? Make sure to write the balanced chemical equation. Okay, so going back to quantum numbers, okay, we should have seen that this element here is in the, let's see, it's in the fourth energy level because it has a principal quantum number of 4. It's in the p block. So the p block is 1, 2, 3, minus 1, 0, plus 1. And it has a positively spinning electron. So this would be the first element in the p block at the fourth energy level, which gives me gallium. Okay? Gives me gallium. So that's, if you got that, you got your first point. Gallium is going to oxidize to form a 3+ ion, and it's going to react with iodate to form gallium iodate. There's 3 iodates here, so to balance this equation, I need that. This is what you needed to get the other 2 points. A balanced equation showing me the reaction and the final chemical compound. And then what do you call this guy? Well, it's an ionic compound, so it would be called gallium iodate. If you got this last part, you got full credit for this question. Okay, that's it. That's all you had to do. Okay, guys, that's it of the video.